Welcome to MarkScheme. We're starting a level mathematics, Pure 1. And our very first chapter is Quadratics. It's a big chapter, so we'll cover it in parts, making sure nothing gets missed. Let's start right from the basics and build it up properly. First, what actually is a quadratic? Look at this. If you just have x, like y equals x, the graph is a straight line. But the moment you square the x, y equals x squared, the line bends. It curves into this shape, called the parabola. That x squared term is what does everything. So a quadratic is any expression with an x squared in it. A x squared plus bx plus c. And there's one condition. A can't be 0. Because if a is 0, the x squared disappears, and you're back to a straight line. Now, why do we actually care about these? Look closely at any parabola. It always has one special point, either the very highest or the very lowest. We call it the turning point, and this is where quadratics become powerful. Where is a company's maximum profit? What's the minimum cost to make something? How high does a ball go before it falls? Every one of these is answered by the turning point of a parabola. So really, quadratics are the mathematics of finding the best or most extreme point. Here's something important. The same quadratic can be written in 3 different forms, and each one is like a different lens, instantly showing you a different feature of the curve. Let's take one parabola and look at all 3. First, standard form, x squared plus bx plus c. This is how questions are usually given. From it you can read 2 things straight away. The sign of A tells you whether the parabola opens up or down, and c is the y-intercept, where it crosses the y-axis, here at -3. But standard form hides the roots and the turning point. Second, factorized form, a times x minus p times x minus q. This one instantly gives you the roots, where the curve crosses the x-axis. Why? Because if either bracket is 0, the whole thing is 0. Here, the roots are at x equals 3 and x equals -1. And third, the star of today, completed square form, a times x minus h whole squared plus k. This instantly gives the turning point at h, k. Why? Because the squared term is smallest when it's 0, and that happens exactly at x equals h, giving y equals k. Here, the vertex is at 1, -4. So, same curve, 3 forms, 3 features, direction and y-intercept, the roots, and the turning point. And because we want that turning point, today we mastered the completed square form. So how do we complete the square? Take x squared plus 6x plus 5. Here's the key idea. We want x squared plus 6 guineas to become a perfect square. Now x plus 3 whole squared expands to x squared plus 6x plus 9. So x squared plus 6d is almost that. That does. It's just missing the plus 9. So we add 9 to complete it, then immediately subtract 9 to keep it equal, and bring down the plus 5. That gives x plus 3 whole squared minus 9 plus 5. Quick rule. Take half of the x coefficient. Half of 6 is 3. That goes in the bracket. Then subtract its square. 9. Finally, -9 plus 5 is -4. So the answer is x plus 3 whole squared -4. Now the payoff. When a quadratic is in this form, a x minus h whole squared plus k, the turning point is simply h, k. Here's exactly why. The squared part, x plus 3 whole squared, can never be negative. The smallest it can ever be is 0. And it hits 0 when x equals -3. At that moment, y equals -4, the lowest the curve ever gets. So the turning point is -3, -4, the minimum value is -4, and the line of symmetry runs straight through it at x equals -3. Look at the graph. That's exactly the bottom of the parabola. But why is it actually called completing the square? There's a beautiful picture behind it. Think of x squared as a literal square with side x. Now, plus 6x, split it into 2 equal pieces, each 3 eggs, and attach them to 2 sides of the square. Look what happens. One corner is left empty, exactly a small 3 by 3 square, which is 9. The moment we fill that corner, we've built one big, complete square, with side x plus 3. So x squared plus 6x plus 9 equals x plus 3, whole squared. And that's why x squared plus 6x equals x plus 3, whole squared, minus 9. Completing the square. Literally completing a square. Now, a real exam question. Express 2x squared minus 12x plus 19 in the form a, x minus b, whole squared, plus c. The new challenge. The coefficient of x squared is 2, not 1. And completing the square only works when that coefficient is 1. So step 1, we factor the 2 out. But only out of the x squared and x terms. That's 2 times x squared minus 6x. We leave the plus 19 completely alone outside the bracket because we don't want to touch the constant yet. Now inside the bracket, we have an ordinary x squared minus 6x. So we complete the square just like before. Half of minus 6 is minus 3. And we subtract its square, 9, giving x minus 3, whole squared minus 9. But careful, that whole bracket is multiplied by 2. So we now multiply the 2 back through everything inside. 2 times x minus 3 whole squared, and 2 times minus 9, which is minus 18. Bring down the plus 19. Finally, minus 18 plus 19 is 1. So the answer is 2, x minus 3, whole squared, plus 1. And read what it tells us. The smallest the squared part can be is 0 at x equals 3. So the minimum value is 1. And the turning point is at 3, 1. That's the whole power of this form. So today, we built it up properly. What a quadratic is, why it matters, the 3 forms, and what each reveals, and completing the square, which hands us the turning point directly. Next, in part 2, the discriminant, b squared minus 4 ACZ, which tells us how many solutions a quadratic has. And to check your past paper answers against the official MarkScheme, head to markscheme.app. See you in part 2.